All right, so let's talk about important things for review. So if the derivative of a function is positive, that corresponds to a function increasing. If it's negative, it corresponds to a function decreasing. So in other words, information about the derivative gives us information about the function. But also information about the second derivative gives us information about the function. So for instance, if the second derivative is positive, then we say that the function is concave up, which means it's bending up. So it's doing something along the lines of this. If the second derivative is negative, our function is concave down, so it's bending downwards, doing something along the lines of that. So information about the derivative gives us information about the function, how it looks, which is useful if we want to, for example, draw the function, which is what we started talking about last time. We also talked about what an inflection point is, and it's simply a point where concavity changes. So how do you find inflection points? Well, it's a lot like finding critical points. You take the second derivative, set it equal to 0, or say where it's undefined. And basically, those are kind of like critical points for the second derivative, and then you just say, does concavity change when you cross? Now, you can use the second derivative for a couple of things. One, it tells you about concavity, but concavity tells you how your curve is shaped, which also gives you information about what's happening near your critical points. And it leads us to what's called the second derivative test. And this is a test to determine whether a point is at a max or a min, or neither. Now, in this case, the second derivative test can't tell you neither. But it can sometimes help you identify max or min. It's a little bit weaker in some sense than the first derivative test. It says if your first derivative equals 0, so if it's undefined, you can't even bother with the second derivative test. It doesn't work. But if the first derivative exists and it equals 0, and the second derivative exists, then one of the three following facts is true. Either it's positive, so the second derivative being positive, if you might remember, we drew some shapes here. So the second derivative being positive means the curve looks like this, and so we're at a min. If it's negative, so our second derivative is negative, so our curve looks something like this, so it means we're at a max. And if it's 0, this is the worst situation, because if it's 0, we don't know what's going on. So it's an inconclusive result. It's not a neither result. It could be a max, it could be a min, it could be neither. And so when you get to this, you have to do some more work. Usually you go back to the first derivative test. You can do some various other things, but usually that's what happens in that case. Now we're jumping into curve sketching, which is the other topic we talked about last time. And curve sketching is sort of a lost art. It used to be taught a lot more frequently. And hopefully if you had a good pre-algebra course, they did some curve sketching in there. And a lot of what we're doing in curve sketching is just what you learned in pre-algebra. Really, the only thing that's different with calculus is just that we're better at finding interesting points. So how do computers draw curves? Well, they draw curves by just plotting a bunch of points and then just connecting them. Now, of course, they plot enough points that when they connect it, it doesn't look like straight lines connecting them. It looks like, just almost like there's a real curve. Now, how are we going to do it? Well, we're going to basically do the exact same thing. What we're going to do is we're going to plot some points. But instead of plotting tons of points, we're just going to plot a couple of points. And we're going to say, what are the interesting points? Of course, definition of interesting, what does that mean? Well, we're going to include a couple things. Critical points, but really we're going to focus on max and mins are the important things with critical points. And what's important about critical points is that it tells you something about the transition of your behavior for your derivative. So for instance, your derivative was positive, then it was negative. That's an example of what happens at a max. Or it was negative, then it was positive. Also inflection points. Now this tells you something about what's happening with the second derivative, how the second derivative is behaving. So these 2 points combined are what the book calls transition points. In other words, something is happening. Your behavior is transitioning at these points. And in particular, behavior with respect to the derivatives, first or second derivative. Some other points which might be interesting are intercepts. For example, where it hits the x-axis or where it hits the y-axis. And asymptotes. For our class, mostly when we talk about asymptotes, it's going to be a vertical asymptote, something where you have a non-zero number on the top and a 0 number on the bottom. So you have a division by 0 kind of problem. There are other ways to get vertical asymptotes, of course. And then there's horizontal asymptotes. And I don't want to spend a lot of time on this. Let me just help you feel more comfortable by telling you there's no curve sketching on the midterm. So I'm not going to ask you to draw a picture for the midterm. There are some problems where drawing a picture might help you, but you won't actually have to draw a picture. So let me quickly talk about asymptotes. Most of the time when we have, say, on your homework, for instance, we're going to be looking at asymptotes. what you're looking at is what happens to the limit as you approach infinity, either positive infinity or negative infinity of your function f of x. If it goes to some number, that's what we call a horizontal asymptote. It's approaching this value. Say it's equal to k, where k is some number. Now, this is what we mean by horizontal asymptotes. How do you find them? Generally speaking, we're going to look at very simple kinds of functions. We're going to look at functions which are polynomials over polynomials. And the moral of the story is you simply need to see what's happening with the highest powers of your polynomials. The highest power of your polynomials will basically tell you the whole story. So you really have two polynomials. So for instance, suppose I want to know what's happening. Let's just make something up. 3x cubed plus 5x squared minus 2 over x plus 7. Suppose I ask you what's happening to this as x goes to plus or minus infinity. Well, really, as x gets large, the important terms are these terms here. Because the 7 gets insignificant compared to the x. The 5x squared minus 2 is insignificant compared to the 3x cubed. And you say, OK, what does this really look like? Well, it really looks like 3x cubed over x, or 3x squared. So you say, well, this is blowing up. Now, to be more rigorous, how do we do it? Well, you look at it and say, OK, suppose here we have a cubic. So the highest power is 3 on the top. First degree, highest power is 1 on the bottom. And whatever power is smallest, in this case, the x, I'm going to multiply top and bottom by 1 over x. Now, this is how we would do it if we were being rigorous. Intuitively, you just look at the leading coefficients. But what happens when I do that? Well, I still have the same limit. Because I multiply top and bottom by 1 over x, I really multiplied by 1. So I don't change the value of the limit. This is the same thing we did when we multiplied by conjugates. So on the top, I just divide everything by an x, 3x squared plus 5x minus 2 over x. And on the bottom, I just get 1 plus 7 over x. And now here's the fun things. What happens? Well, what happens is on the bottom, what do you approach? You approach 1, because that 7 over x basically disappears. So on the bottom, you're just approaching a constant. And what happens to the top? Well, as x gets bigger and bigger, what happens to these values? They get bigger and bigger. Yeah, so this is going to infinity in this case. It turns out positive infinity, but it doesn't really matter. So in this case, this is an example of where something blows up. Now, we might have had something different. Suppose I have something where I do a limit as x goes to plus minus infinity, and you have 5x squared plus 7 over 3x to the fourth plus 9x. Again, looking at the highest powers, really, I just need to understand what's happening with the 5x squared and the 3x to the fourth. In this case, the highest power is in the denominator. But I'm going to do the same trick where I say, OK, well, I'm going to multiply by 1 over something. And in this case, let's multiply by 1 over x squared. Now, the reason I want to multiply by 1 over x squared, if you think way back to when we did limits, essentially what's happening is we have an infinity over infinity. And I want to sort of slow it down so I don't get infinity over infinity. That's my whole goal. That's the game I'm playing. It's like I'm trying to avoid infinity over infinity. By multiplying by 1 over x squared, I'm able to slow either the top or the bottom, or both, down so I don't have that problem. And once I get out of the infinity over infinity, I can just look at it and say, aha, I see what's happening. Well, again, when I multiply by 1 over x squared, I get 5 plus 7 over x squared over 3x squared plus 9 over x. Now what happens? Well, on the top, this goes to 5, which is a number. What happens to the bottom? Yeah, it goes to infinity. It gets infinitely large. This is going to huge. Or if you like, infinity. So if I have 5, or a number basically very, very close to 5 for x large, over a really huge number, what does it look like? It looks like 0. It's small. Yeah, it goes to 0. So in this case, when the power on top is smaller than the power on the bottom, it just goes to 0. The bottom is dominating. But of course, the most interesting example is suppose the powers on top and bottom match up. So you have 3x squared plus 5 over x squared plus 7x. again, just focus on the leading terms. What does it look like? Looks like 3x squared over x squared, which we would call 3. Now, if we were being rigorous, multiply by 1 over x squared over 1 over x squared. And this becomes limit, as we approach plus or minus infinity, of 3 plus 5 over x squared over 1 plus 7 over x. And lo and behold, you just think about what happens to the 5 over x squared and 7 over x as x goes to infinity. Our negative infinity are the 1. They vanish. They go to 0 for large x, and we're just left with 3 over 1. So it's 3. So really, when we talk about horizontal asymptotes, I'm only going to be looking at very special functions. And I'm going to say, OK, what happens as x gets large? So you look at the coefficients of the leading terms, leading powers. So very, very simple. So if you can do that, that's asymptotes. OK, so now what we've done, we found our interesting stuff. We found points, we found asymptotes, we found intercepts. Now we plot the interesting points. We plot these points. And then we say, OK, so I found these points. And in between these points, I know something. I know that the derivative is going to have the same sign. And I know the second derivative is going to have the same sign in between two consecutive points. And I say, OK, so I know roughly what the shape will look like, because I have this very simple rule. If my derivative is positive, my second derivative is positive, it has to be doing something like this kind of behavior. My derivative is positive, my second derivative is negative, it has to be doing something that looks like this kind of behavior. My derivative is negative, my second derivative is positive, has to be doing something like this kind of behavior. And if my derivative is negative, my second derivative is negative, has to be doing something like this kind of behavior. These are the 4 possibilities, the 4 possible sign combinations. And so what do? Well, we just play connect the dots using the right shape. It's not very hard. So before we do a quick example, because I don't want to spend too much time, let me just point out that we can answer some of the questions without even having to do any calculus. All this was algebra stuff. So for instance, here is a problem from the book where they give you these 4 curves, and you have to play matching. Let's see, where can I write the functions down? So they have 4 functions, and they give you 4 pictures, but they don't tell you which picture goes with which function. They want you to figure it out. So the 4 functions are 1 over x squared minus 1, 1 over x squared plus 1. Let's see, what else we have? We have x squared over x squared plus 1, and x over x squared minus 1. So let's see if we can just, without doing any calculus, see if we can answer this question. So for instance, if I see this function, 1 over x squared minus 1, what are some things I can say about the function? Do they have any asymptotes? OK, how about horizontal asymptotes? What's the horizontal asymptote going to be? It's going to be 0. This doesn't have horizontal asymptote 0. We can throw this one out. Does it have any vertical asymptotes? Yes. Where are they? 1 and -1. Now, this doesn't have any vertical asymptotes, so we can throw that one out. OK, so these 2 pictures are possible candidates, because they both have a horizontal asymptote of 0 and vertical asymptotes of 1 and -1. Now, can we figure out which one it is with doing one little test? Well, yes, of course. Otherwise, I wouldn't ask. Leading question. Can we do it, and how do we do it? Well, what are some things we can do? We can just plug in a single value for x. Suppose I plug in x equals 0. What value do I get out for y? -1. Now notice that here, 0 crosses through the origin. So that says when I plug in 0, I get 0. So this can't be right. So this is the right one. So this, oh, my chalk is over here. So now this is the 1 over x squared minus 1. OK, how about this one? Which one will this one be? Yeah, this also has the same asymptotes. So I still have to be divided by something like x squared minus 1. And there's only one other one. OK, so how do I distinguish these 2? Well, they kind of look like they flipped upside down one another. But what's the big difference between them? One of them has a horizontal asymptote of 1. One of them has a horizontal asymptote of 0. And I'm left with these 2 functions here. Which one has a horizontal asymptote of 0? 1 over x squared plus 1 or x squared over x squared plus 1? Yeah, 1 over x squared plus 1, because the bottom is going to dominate. So that this is the 1 over x squared plus 1. And that just leaves us with this. And then we can convince ourselves, yeah, this looks right. Because it has a horizontal asymptote of 1, because if you look at the leading coefficients, they match, the powers match. So it goes through the origin. It's always positive. Yeah, okay. So that's an example of a homework problem. Very, very easy. All right. We should go work through one example. I don't want to spend too much time. Let's plot something that's very similar to one of those pictures. Okay, we'll do one at very fast speed. All right, suppose I ask you to plot x over x squared plus 1, this function. Let's go through and identify interesting points. Let's first talk about asymptotes. Are there any vertical asymptotes? Can the denominator ever be 0? No, because you're squaring something and you're adding one, that's always going to be positive. So there's no vertical asymptotes. Are there any horizontal asymptotes? There is. What's the horizontal asymptote in this case? Well, you compare powers. Power on the top is x. Power on the bottom is x squared. So the bottom is going to be the dominating one. So it's really going to look like 1 over x for x large. So this says horizontal asymptote looks like y equals 0. Okay. How about intercepts? Where does it hit the x-axis? Well, if it hits the x-axis, that means the numerator had to be 0. When does that occur? When x equals 0. Okay, what's the y-intercept? Same point. Because you plug in, to find the y-intercept, you plug in x equals 0, and lo and behold, the x-intercept and the y-intercept in this case are exactly the same point. So we know it goes to the point 0, 0. All right, now let's find our critical points and inflection points. So how do you find critical points? Well, take the derivative. So we take the derivative of the top times the bottom, using the quotient rule, minus the top times the derivative of the bottom, divided by the bottom squared. Simplify that, it becomes 1 minus x squared over x squared plus 1 quantity squared. Okay, this is never undefined because the denominator is never 0. When does it equal 0? Because that's the other kind of critical point. Well, it equals 0 when the numerator equals 0. 1 minus x squared equals 0, which is at what? Well, 1 and negative 1. Okay, so we know that we have critical points at 1 and negative 1. So I'm going to just quickly mark negative 1, 1. Let's use our first derivative test to figure out what's going on. So our first derivative test is if we plug in a value and we see whether it's positive or negative. So let's plug in a value. What's the number between negative 1 and 1? 0. 0 is a nice number. Plug 0 in, we get 1. That tells me something about the derivative. It says y prime is positive. Or in other words, between negative 1 and 1, my function is increasing. What's the number below negative 1? Negative 2. 1 minus negative 2 squared is a negative number. Negative 2 squared plus 1 is positive. Number squared, that's positive. So whatever the value is, I don't care about the value. I only care about the sign. It's easy to check. It's negative. So it's a negative value below negative 1. And also, similarly, if you plug in 2, you'll see same thing. It has a negative value above 1. All right, so really bad sketch. We go down, we go up, we go down. So what can we say about negative 1? Yeah, negative 1 is a min. What can we say about 1? It's max. Okay. So that we found our critical points. How about inflection points? Well, how do you find an inflection point? Second derivative. Okay, so second derivative is the derivative of the first derivative. So we take the derivative of the top times the bottom minus the top times the derivative of the bottom, which we do the derivative of the bottom using the chain rule. All over the bottom squared. Well, x squared plus 1 squared squared is the same as, let me just use that, say this, x squared plus 1 to the fourth. Now everything has an x squared plus 1, so I'm going to cross out a single x squared plus 1, make that cube. Now if I multiply this out, I get minus 2x cubed minus 2x, then minus 4x plus 4x cubed. all divided by x squared plus 1 cubed, which I can rewrite this again. This is 2x cubed minus 6x over x squared plus 1 cubed, which I can factor this. This is 2x times x squared minus 3 times x squared plus 1 cubed. All right, now, it's never undefined. When does it equal 0? Well, it equals 0 when the numerator equals 0. So we get that the second derivative equals 0 when x is either 0 or x squared minus 3 equals 0, which is at root 3 and negative root 3. So if I come back here, let me erase some of this. I'm going to draw a line similarly as I did here. Now 0, of course, we already know where that is. Here's 0. Root 3 is bigger than 1, so it's somewhere out here. And negative root 3 is smaller than negative 1. OK, so here's negative root 3. Just want to compare the two. All right, now let's quickly check to see whether these are actual points of inflection. How do we check to see if they're points of inflection? Well, if I hadn't erased it, it would be right here. An inflection point is where we change concavity. So I just check to see if the second derivative changes sign. So I'm going to do the same thing where I plug in points. What's the point between 0 and root 3? 1. I plug 1 in. What do I get? I get 2 times 1 times 1 minus 3. So the numerator will be negative, and the denominator is always positive. So this tells me that between 0 and root 3, the second derivative is negative. Now what if I plug in negative 1? Well, I have 2 times negative 1 times 1 minus 3, which is negative 2. So now it'll be a positive over positive, so that my second derivative is positive. And what's the number bigger than root 3? 2. It would be 2 times 2 times 2 squared minus 3, which is 1. So it'll be positive on the top, still positive on the bottom. So my second derivative is positive here. And similarly, it's going to be negative over here. OK, so these are, in fact, all points of inflection. And so now we're in good shape. So we found our critical points. Where we found where our first derivative changes sign at negative 1 and 1. We also found our inflection points where the second derivative changes sign at negative root 3, 0, and root 3. So we come now to draw our picture. And we know 0, 0 is a point. We now want to put a point on every one that we found that was interesting. So negative 1, negative root 3, 0, 1, root 3. So we already put 0. If I plug in negative root 3, all right, if I plug in negative root 3, what value do I get? Well, root 3 squared is 3, plus 1 is 4. So I'm going to end up with a point here, which is at negative root 3 over 4, which is smaller than 1. If I plug in negative 1 to my function, I get negative 1 over 1 squared plus 1, negative 1 squared plus 1, which is at a half. And in relationship, it'll be somewhere roughly here, negative a half. And symmetry, this will be at roughly a half, and this will be at root 3 over 4. And now we just play our connect the dots. Oh, one other thing we should mark is we have this horizontal asymptote, which works for large values of x. So for large values of x, I should get close to y equals 0. Now, below negative root 3, I know my derivative is negative, and my second derivative is negative. So it says I'm doing something like this. So my curve will look something like this as I come into my point. Now, what happens? My derivative is still negative, but now I switch signs for the second derivative. So my concavity changes. So now I go from this kind of behavior to this kind of behavior until I hit this point. And I should say at this point we're at a min, so that it's going to have a flat tangent line. Now I switch my first order behavior, it becomes increasing. So I'm now going up. I'm still concave up until I hit this point at 0. Then after 0, I'm still increasing, but now my concavity changes to be negative. So now I'll be increasing, and let's see, have negative concavity, which is this case over here. So now I'll be something like this. And then again, I have a flat tangent line. Now what's going to happen is my derivatives now become negative, but I'm still concave down. So I'm going to do something like this. And then finally, my derivative will be negative, but I'll be concave up, and I have to approach this line. And there you go. There's a graph of x over x squared plus 1. OK, and now you can see why I don't want to do this on a test, because it takes 20 minutes just to do one of these. And there are much more fun problems to do that takes 20 minutes. So let's go to our next section. So our next section is called optimization. It calls it applied optimization, but it's optimization. So what is optimization? Well, you look at the word, it has the word optimize. Well, actually it has the word optimiza, but we'll pretend like it's just a better way of spelling optimize. So you're trying to find the optimal value of something. In other words, you're trying to maximize or minimize something. So you maybe want to try to maximize your area. Maybe you want to minimize your volume. Maybe you want to maximize your profit. Maybe you want to minimize your costs. There's all sorts of things that you could try to maximize or minimize. And these are important questions. I mean, we're trying to get the most out of what we have. So how do we go about doing it? Well, it's very easy if you think about it, because what have we learned? We've learned how to find max and mins. That's what we've been developing. We've been developing tools. We know how to find max and mins. We know how to do it because we have these tests, first derivative and second derivative tests. So we're going to use calculus to answer these kinds of questions. And what's the basic idea? Okay. Well, the basic idea is to find a function which represents our problem. In other words, we're asked to maximize or minimize something. We want to find a function which represents what we're trying to maximize or minimize. So if we're trying to maximize area, we find a function that represents the area. Find a function representing what we are trying to optimize. And there's one little trick here. Let me just mention. I won't say it's a trick. Just be careful here. Of a single variable. This is our first time we've actually used the word single variable in our class, even though our class name is single variable calculus. I should point out we've only been dealing with one variable at a time. Now there's another class called multivariable calculus, which is the next series up. And that's how you deal with more than one variable. We haven't learned those tools. So if you're doing an optimization problem, say, for example, on a midterm, make sure you do it using single variable, because we're going to shake our heads and say, why are you trying to do multivariable stuff? You shouldn't be doing that. You haven't learned it yet. But that's the basic idea. We find a function and then use calculus to find max min. I mean, we already developed the tools. There's no new tools here. This is the stuff we've already learned. The only thing that's different is now we're just applying it to something which is actually useful, depending upon your perspective. All right. Now, what's the hard part about this? Well, using the calculus to find max min, that's pretty straightforward. We've had a lot of practice about doing that. There's nothing really new there. So most of the problem here is to find that function. And this is going back to sort of the related rates kind of thing. How do we do that? Well, some things that help are draw a picture, if you can. If you may not be able to. But sometimes if it's a problem with geometrical interpretations, it helps to draw a picture. You want to label your various quantities. So, for instance, What do I mean? Essentially, you should have two variables in the end. One variable is what you're trying to maximize or minimize. The other variable is what you can change. What do I mean by that? So, for instance, suppose I'm asking you to maximize your profit. Well, what can you change to maximize your profit? Well, you only have control over one thing, and that's how much you're producing, your quantity. So what you do is you say, okay, my two variables are my profit and quantity. And I want to write profit as a function of quantity. And then you take a derivative, and you solve. All right, so draw a picture, label various quantities, and you just practice, practice, practice. I don't know if there's really much more to that. So let's just do a bunch of examples. Okay, so here's a simple example. Suppose you're a manufacturer of cans. And you're asked to manufacture a can. And by the way, if you remember what I mean by can, it's basically a cylindrical thing here made out of metal. You're asked to manufacture a can which has 16 pi inches cubed volume. So you have to have 16 pi cubic inches of volume in that can. But you can make it any shape you want. And what I mean by that, you can pick the radius, you can pick the height, you can do it whatever you want. It just has to have that much volume. So you can make a really flat can, which is really wide. You can make a really tall, skinny can. You can do all sorts of stuff. Well, you think about it for yourself. You say, well, look, I have to pay for the metal to make this can. So I want to use as little metal as possible. The less metal I use, the cheaper it is for me to make, the more profit I get. So what's a good question I can ask here? If I'm making these cans, well, what dimensions minimize the surface area? Because the surface area tells me how much metal I had to use. Oh, what dimensions? I forgot to put the word minimize. Minimize the surface area. Okay. Now, this seems like a reasonable question, and it's always good to ask yourself, is this a reasonable question? And it is. Now, let's start thinking about it here. Well, what do we know about it? We have to have 16 pi cubic inches of volume. What's the volume of a can? Well, so far we haven't put any labels on it. Let's start labeling stuff. So for a can, there's two important dimensions. There's how big the radius is of the circle on the top and bottom, and how high it is. So what should we call the radius? R. Yeah. We're not very creative. And R is good because it helps us remember R is for radius. If we called it Bob, we might forget what Bob stands for. We can call it whatever we want. But choose labels which are convenient for you to help you remember what's going on. R is easy for us to remember what's going on. R, radius, aha. How about this distance for height? H, yeah, nobody went with Alice. They went with H. Okay, good. H for height. It's useful to do these things. Now, what's the volume of this can? Well, what's the area of the circle? Pi r squared, right, pi r squared. And essentially what you do is you just think of it as the area of a circle, and you just go straight up and down. So the volume of a can is pi r squared h. Okay. So we know that we need our volume to be pi r squared h. But we also know we have to have a specific volume. So this V, that's a general volume. But for our case, we know that we need to have pi r squared h has to end up being 16 pi. So this is our constraint. We're trying to maximize given some constraint. In this case, this is a relationship between R and H. Now, what is the surface area? Well, first off, what's the area of the circle? Pi r squared, yeah. That's not a trick question. Pi r squared, very good. There's two circles, so 2 pi r squared. This is the top and bottom. All right. So we found the surface area of the top and the bottom. But we also have to have the surface area of the side. Now here is where we come through with our visualization. Pull out our industrial strength scissors. Okay, cut it open. When we lay it flat, it looks like this. Looks like a square. Now, how high is the height? It's h. How wide is it? It's the circumference of the circle. What's the circumference of a circle? 2 pi r. So what's the area? 2 pi r h. So this is the side. Okay, good. Now we have our surface area, which we're trying to minimize or maximize. In this case, minimize, even this constraint. Now, what's our problem with this function? It has two variables. It has r and h. And remember, we need to get down to single variable because we haven't learned multivariable calculus. That's in a couple quarters. We're going to rock that class when we get there. But for now, we can't do it. So we're like, oh, great. Now what are we going to do? Well, we do know something about an r and h. They're not arbitrary. They're not independent of one another. This gives us a relationship between r and h. So let's just solve for r in terms of h, or h in terms of r. So in this case, do I want to solve for h as a function of r, or for r as a function of h? You can do either one. You'll get the same answer. So in this case, there's not a wrong answer. But that said, there is a right answer in this case. The reason I say there's a right answer is, which one is easier to solve for? H. Because if you solve for r, what are you going to end up having? Square root. We hate square roots. Don't want them. Okay, so let's solve for h. The pi's cancel. H is 16 over r squared. Now we throw that into our equation. And we get that the surface area is 2 pi r plus 2 pi r times 16 over r squared, which is 2 pi r plus 32. Thank you. 32 pi r squared plus 32 pi over r. Now we're down to single variable. Now we use our techniques of calculus. So I really should say surface area. Now I really think of the surface area as a variable, as a function of the variable r. I got it down to single variable. Okay. Now I should just point out, of course, r is going to be positive. R and h are going to both be positive. We're not going to have a negative length. This is just sort of implicit to the problem. But we'll write it down. All right. So what's our next step? Well, we take the derivative of surface area. What's the derivative of 2 pi r squared? 4 pi r. Yeah. Because we're taking the derivative with respect to r. R is our variable. Wherever the variable is, that's what we take with respect to. R can change. So the 2 comes down, r to the 1. What's the derivative of 32 pi over r? It becomes actually a negative 32 pi over r squared. Now, how did we do that? Very easy. Using my fancy chalkboard technology, I can rewrite 32 pi over r as 32 pi times r to the minus 1 power. The minus 1 comes down. That's where the negative comes from. And then it becomes r to the minus 2, r over r squared. Now, remember, we only care about r greater than 0. So this is defined for r greater than 0. There is, of course, the problem at r equals 0, but we've already tossed that out. So our only critical point is going to come from where our derivative is equal to 0. So in this case, we have 4 pi r cubed equals 32 pi. Just okay. Here, let me do that in 2 steps, in case anyone's wondering. 4 pi r equals 32 pi r squared, 32 pi over r squared. Now multiply both sides by r squared. Divide both sides by 4 pi. We get r cubed equals 8. So what should r be? Oh, that sounds like a chain, doesn't it? RB. Makes me hungry. I haven't had lunch yet. R equals 2. Okay, so now we know that r equals 2. If r equals 2, what should h be? Well, 16 over 2 squared. equals 16 over 4 equals 4. Okay, so we have a guess. R equals 2 and H equals 4. Now, in this case, we knew we were going to get an answer out. We only got one, so we know it's the right answer. But to be rigorous, what should we really do? We should check if it's actually a max. Maybe we did something incredibly stupid and found like the worst possible can you could possibly make. And we're just going to go bankrupt because we make this really lousy can, and everybody's laughing at us. It's like, ha, those idiots, they don't know how to make good cans. They found the max when they were looking for the min. Dorks. Okay, so how do we check if it's actually the min? Yeah, right, because we set the derivative equal to 0 because we're looking for critical points. Then we set the derivative equal to 0 to find the critical points. We always find critical points. Now, that's a good question. What if I ask what dimensions maximize the surface area? Well, notice that basically here, this is the surface area for any r. Now, give me an r, I can generate a can with that area. Sorry, yeah, with this surface area, which has 16 pi. But what do you notice about this function as r gets large? The surface area gets huge. And in fact, I can make a really stupid can where I have like a huge circle, a little tiny height, and another huge circle on the bottom. And it has 16 pi cubic inches, but it's really stupid. I mean, you're wasting tons of metal. So in this case, when you try to ask what's the maximum, there is no maximum. You can get arbitrarily large. You can make like a 5-ton can that has 16 cubic pi inches worth of volume in it. So you have to make sure. Okay, so let's quickly check. R equals 2. Well, we know we want to be bigger than 0. Here's 2. Let's use the first derivative test. We could also have used the second derivative test, but let's use the first derivative test. What's the point below 2, above 0? 1. And if I plug 1 into my derivative, yes, that's right, there it is. If I plug it in 1, I get 4 pi minus 32 pi. So that tells me that my surface area, right here, the derivative is negative, which means I'm coming down between 0 and 2. Now what if I plug a number bigger than 2? Let's say 4. 4 squared is 16. 32 pi over 16 is 2 pi. 4 pi times 4 is 16 pi. 16 pi minus 2 pi is certainly positive. So my derivative of my surface area is increasing. So in fact, 2 is good. 2 is at the min. So now we're like, yes, this is it. So you want R to be 2. You want H to be 4. Now, you might ask, wait a second, that's kind of a weird-shaped can. I don't ever see those kinds of shapes of cans when I go shopping at the supermarket. That's true. You probably don't. Because, we just made a very simple thing. The question was, how do you minimize the surface area? When you make cans for a living, you'll discover things like the top and the bottom of the can cost you more than the sides. So you have to factor all this in. How much does the top and bottom cost, and how much does the side cost? And various constraints will give you different shapes. Yes?
Double check, make sure it's known, because we also done H and 4 instead of R and 2, like with the first derivative test. We've used 4.
Well, we don't have this function as a... Well, for H equals 4, we have it as a function of R. Now, we could go through and do the exact same problem all as a function of H. We get the same answer. So, yeah, you could definitely check that again if you really like punishing yourself. I'm sorry, I shouldn't say punishing yourself. That makes it sound bad. Okay. All right, let's see. Perhaps we can do one more before time expires. So this is a sort of a classical problem. So suppose you have a river, and we know it's a river because we're going to put blue in it, indicating this is a river. You own a large piece of land, and you happen to raise chickens. And you want to put up sort of like a little fenced-in chicken area. Now, you don't need anything for the river because chickens don't like to swim. But you need to put fencing along the other side. So what you're going to do is you're going to make some rectangular fencing here. And here's going to be your chicken area, where chickens run wild and free. Now, you happen to have some fencing. You happen to have 400 feet of fencing. what you're going to do is you're going to give your chickens a really nice area. So you want to try to give them as much area to play in as possible. So what is the maximum area you can give to your chickens? So we have to use our 400 feet of fencing. That's all the fencing we have available. We have to put fencing on the side here, but not on the river side. How much area can we give to our chickens? What's the maximum area? All right, so how do we do it? Well, let's label stuff. This is a rectangle. What do you want to label this side? X. Okay, since it's sort of in the X direction. How about this side? Y. And what is it we're trying to maximize? The area, which is X times Y. Very easy, rectangle. But we haven't taken into account our constraint. There's 400 feet of fencing. What does that tell us about X and Y? Yeah, if I add up X plus Y plus another X, 2X plus Y, that should give me 400. So now what do? Well, I need to get down to a single variable. Because right now, area is a function of two variables. But I can do that really simple because, look, I can solve for instance, I can solve for Y. Y is 400 minus 2X. So that my area, which I can write now as a function of X, is simply X times 400 minus 2X. Or this is 400x minus 2x squared. So now what do? We use our calculus. We've gone it down to a function of a single variable. We just do our optimization. A prime of x is 400 minus 4x. There's no critical point. It's never undefined. There's a critical point. The only critical point comes when it's equals 0. So 400 minus 4x equals 0. So what should x be? 100. So that says that you should put 100 in for x. If 100 is x, so there's 100 feet here, 100 feet here, how much is left for y? 200. So what's the area? Well, 100 by 200 is 2,000,000, or 20,000 square feet. Now, the last thing we should really do is check to see that this is actually at a minimum. Let's do the second derivative. What's the second derivative of this function? -4. Notice it's a constant. And it's negative, which means we're always concave down. So at our critical point, if our second derivative is negative, it is a max, which we were looking for. So that's good. All right. We'll do a few more next time. As a reminder, the midterm will go up to what we talk about next lecture. So up to next time, not next Wednesday's lecture.